Hello together. Before I want to do the simulation of our gallium arsenide field effect transistor and have a look to the stability circles, I want to discuss with you three different situations. Here I sketch the stability circles in the load plane, and in principle we can distinguish three situations. So we have in the load plane, we speak of one thing is the right half plane or the left half plane. In the right half plane we have always that the load conductance is greater than 0, and in the left half plane we have that the load conductance is smaller than 0. So we have first the situation that stability circles lies totally in the right half plane. And of course, as soon as I take a load admittance out of the circle, of course in this situation it has a positive real part, and so this means as soon as I take the load admittance out of the inner part of the circle, our system may become stable. So there's another situation where we have that the stability circles is part in the right half plane and part in the left half plane. So if I have now take a load admittance out of the red section of our circle, then of course again in this region the load conductance is greater than 0. This corresponds to a real load admittance. But all parts of the load admittance which lie in the left half plane, this would be, they have a negative real part, but in a real load admittance will never have a negative real part. So, and now we can have a look to the third situation where the stability circle lies totally in the left half plane. That would mean our circuit only becomes unstable if I have a load which has a real part which is smaller than 0. But this is normally not the case. So in this situation our system is stable. And now we can have a look and go and discuss the stability factor or define the stability factor. In this situation we have here the center of our load stability circle and here the radius of our load stability circle. And since this has a negative value, we can say as soon as the negative center, real part center of our stability circle is greater than the radius, then we have a stable system. And if I insert now these two equations, I end up, I bring this term on this side and so on, and divide by this, then we can say this term here will always be greater than 1, and this we call then the stability factor. Of course, this is only true as long as G11 and G22, they must be both greater than 1. Of course, we can also have a look on the stability factor on a dB scale using this equation, and then we see a stable circuit is defined by a kdB value which is greater than 0. So now we are ready to do our simulation of our gallium arsenide field effect transistor.
Today I want to study again with you the stability circles of a gallium arsenide field effect transistor. We again have here our data set of our transistor, and we have here our network analyzer, and this network analyzer we can use to display the parameters. For example, if I do the analysis, I have here now the parameter S21. And to have a look to the stability circle, we must switch the parameter to Y, for example, 21. And then we use as a format our rectangular plane format. And then we will find the parameter in a rectangular plane. So I reduce the scale and reduce the reference position. So we have here a rectangular plane and we have 0.1 per division. This means we have 0.1 Siemens or 1 over ohm per division. And here is displayed now our parameter Y21. And here you see the curve is displayed, but in the admittance plane we can also have a look now to the stability circles. And first we have a look to the stability circle in the load plane. Here this is the stability circle in the load plane, and here are in this line are given the parameters, the radius and the x and y coordinate of the center and the frequency. And of course what we can do is, for example, we can enhance the scale of this parameter so that the stability circle is more, you see it better in this plane. And what we can do is now, for example, to have a look how this stability circle changes if the frequency is changing. So what we see here is that the stability circle for a frequency round about, we can see here, round about 7.16 gigahertz, it will lie totally in the left half plane. So now the system will be stable at all. And if I enhance the frequency, you see it will still further or move into the left half plane. And perhaps we also change now the parameter again. So I go to the curve again and change the format to the log mag format again. And what we can have a look here now is to the stability factor K. I already explained, and the stability factor K is now given in the dB scale, and here we have the 0 dB line, and we can have a look with the marker function, and we see that for frequencies above round about 7.16 gigahertz, the transistor becomes stable. So here in the region it's stable, but it's unstable for lower frequencies. And now I want to go back to the parameter Y21 again, and we go back to the admittance plane, to the rectangular plane. And here we have the rectangular plane. Now the scale is too big, but I just want to have a look now to the stability circles. Again, here we have again the stability circle in the load plane. I can enhance, of course, again the scale, and we see now if I change the scale, the stability circle will move into the left half plane again. I can change, for example, the reference position. And now I want to switch to the stability circle in the generator plane. Here are now the elements or the parameters which describe the stability circle in the generator plane, and you see for low frequencies it's quite small, but if you enhance the frequency, then it will move to more capacitive values, but also it will move a little bit further into the right half plane. So I will change the scale again. So you will see now, for example, if I go back in the frequency, so here it becomes more clear. If I enhance the frequency, then you see this point moves more into the right half plane, and we will get here the highest value in the right half plane. Here we have now per division 0.05 per division. This means here we have round about 0.04 1 over ohm would be this value, and this defines now the position of the stability circle in the generator plane, where it's reaches farthest into the right half plane, and this we can further use to define a stabilizing load which we can connect to the generator, parallel to the generator admittance, and this I will explain again on the board. The very important value now for the explanation is that it moves round about to 0.04 1 over ohm into the right half plane, and I will now go to the board and explain what we can do now.
So I want to explain now how we can use a parallel resistor at the input to stabilize our transistor. We had a look to the simulation and we had a look to the stability circles in a generator plane, and in principle we saw that the stability circle moves slightly into the generator plane, into the right half plane, and then they move back into the left half plane. So the crucial point is this situation where the stability circle reaches most in the right half plane. And this value in principle defines as 1 G-min, I call this. So we may not enter this region with our generator admittance, because if we enter this region, our transistor may become unstable. So we can have a look to our situation. Here we have our transistor in a given point of operation, and here we have our generator admittance, and now we must fulfill always that the real part of the generator admittance must be greater than this G-min. As soon as it's greater, then it will not enter this region. And now we can split up our generator admittance in two admittances. One I call YG prime, and I additional add to the input G-min at this point. So in this situation we have that the total value is always greater than G-min, which results in the point that the YG prime only must be greater than 0. And in our case we found that the G-min is round about 0.041 over ohm, And since I in a simulation tool can only include resistors, I calculate the corresponding resistor and call him P for parallel resistor at the input, and this is 1 over G min, and this is in our case 225 ohm, or if we have a look, or if we include a smaller resistor, then we include more damping and the margin will become bigger in this region. So now I will show this in the simulation tool.
Now I again want to use the simulation tool to show you how we can use a parallel resistor at the input to stabilize our transistor. So first we have a look to the transistor without any stabilization. We again can do the analysis here and have here the S parameter S21, and for example I want to have a look at the to this parameter at a frequency of round about 2.4 gigahertz. So here we would have 2.4 gigahertz and we can read out a value of round about 10.86 dB here. And we saw in the preceding section that I must use at least a resistor of 250 ohm at the input to stabilize our transistor. What I want to use now, I use a little bit smaller transistor, and not transistor but resistor. And if I use a smaller resistor, then of course I include more damping in the system, which will enhance the stability. So in a first step I just want to show you the influence of this parallel resistor at the input on the parameter S21. At the moment we have still the 10.86 dB, but if I do the analysis now, of course due to the resistor at the input, the gain of the overall transistor with the stabilizing resistor will decrease a little bit. But to now have a look to the stability, we just have a look to the stability factor K in the dB scale, and now we see that the stability factor in the dB scale is in the whole frequency range, it lies above 0 dB. So over the whole frequency range this transistor is now stabilized, and we could start to build, for example, an amplifier with this transistor. But I also want to have here now a look on the stability circuits to show you how the stability circle change. So we go to the Y parameter again and we change to the format of rectangular plane, and we can now have a look to the stability circle, and now you see here it's a zero line, and here we have the left half plane. This means now you see the stability circle move totally into the left half plane. This means again we have here a stable transistor, and if I change the frequency, so you see here that it will at no frequency it will come into the right half plane anymore, which again means that the transistor is stable over the whole frequency range, and now we are ready to build an amplifier with it. For example, in the first step we could go to the Smith chart here, here we now have the parameter S21, and to start with in the Smith chart, we of course could have a look to the parameter S11, and now it depends on the frequency which reflection coefficient we use to match our transistor.